So if you have done discrete mathematics, right? So you know what's a semigroup? So semigroup is, you know what's algebra? How do you define an algebra in discrete mathematics? It has a set of elements which we call as a carrier set and some operators. If that operator is associative on that set of elements, because operator basically defines an operation on the set of elements. Okay? If it is associative on the set of elements, then that algebra is called a semigroup. Plus there are other properties. So that's why we call it as a semigroup operator, in the sense that if you say it's a semigroup operator, automatically it means that it is an associative operator. Okay? You all follow recursive doubling? Any doubts in that? Yes or no, man? Something? No doubts. Fine. So in this part of what today and tomorrow we will learn about carry ripple, carry look ahead adders, and then another very interesting multiplier called Wallace tree multiplier. See, there are many multiplication algorithms that are there in standard books like Booth, all these things. Today when we look at very fast computations, I think a much more parallel multiplier like Wallace tree makes sense. So let us not go and read all the multiplication algorithms ever discovered by mankind. So we will just do this Wallace tree multiplier. So I will teach you this multiplier plus these two adders. I think we have done the carry ripple adder. Even Palakkad, you should have done the carry ripple adder as a part of your digital course. But I will quickly revise that and then go into carry look ahead adder construction. Okay? Right. Now what we need is speed. Okay? I need operations that work very, very fast. Now when we want speed, the speed is determined by, if I take a circuit, how will you define the speed of the circuit? The speed is determined by the delay incurred in the circuit. So how do you measure the delay in the circuit? When I change an input, any arbitrary input, what is the time required for the output to change for the corresponding change in the input? The maximum delay is what we call as the delay incurred by the circuit. So for some input changes it could happen say in 1 unit of time. For some other input it can take 5 units of time. For some other input it may take 10 units of time. Now the delay incurred by the circuit will be 10. It is the maximum of all possible such delays, and that would be called as the delay of the circuit. Okay? And this delay is directly proportional to what we call as the circuit depth. Circuit depth is that, assume that I have identical components in the circuit, say I have NAND gates. I can make an entire circuit using NAND gates, yes, right. Now from the input, from any of the input I will go to the output. There are different ways, different paths in which I could go, and let me keep counting the number of NAND gates that I encounter when I move from an input to an output. The total number of NAND gates, the maximum number of NAND gates between an input and an output is what we call as the depth of the circuit, right. So let us take this very this simple example. So this is one NAND gate. So let us take this input, let us take this input. For this input, okay, let me have one more. I could reach from this input to the output with just two gates, but again there is another part from this input to this output which involves 3 gates. Okay. So the depth of this input is 3, the depth of this input is 3, the depth of this input is 4, this is 4 and this is 3. So the entire depth of this circuit is now Okay. So, this is a circuit. So, the depth of this input is, so there is one part which is, as you see here, which takes 2, while there is another part which takes 3. So, the depth of this is 3, the depth of this is also 3, the depth of this is 4, 4, 4 and 4. So, the depth of this entire circuit is 4. Okay. Now, a very quick way of doing it is what we call as a topological sort. What is a topological sort? We take, so there are, note that in a circuit there are these 6 inputs which I have marked in red here. These are basically called as primary inputs. Primary inputs. They are called primary inputs because they are not driven by any other circuit element, right. Now, let us take all the primary inputs. Let us first remove all the gates that are driven only by the primary inputs. So, this is a gate, these 3 gates for example are driven only by primary inputs. So, right. So, this is basically level 1. Okay. Now, we remove all the level 1 gates now and find out what are all the gates that are now inputless. If I remove these 3 gates in level 1, note that these 2 gates actually become inputless. If I remove off these 3 gates, now this brown gates become inputless. So, those are the level 2 gates. When I remove all the level 2 gates, note that this gate becomes inputless, only this gate. Still this gate has one input here. So, this becomes level 3 and finally this becomes level 4 when I remove the level 3 gate. So, first I remove all the gates which are driven only by the primary inputs and that become level 1. I remove all the level 1 gates and find out who are all shaved completely and I get 2 gates which are level 2. I remove the level 2 gates, I get one more here level 3, I remove that and I get level 4, right. This is called, actually this type of what we do here, this algorithm is called topological sorting. So, what will the topological sorting give you? It will give you gates at the same level and it will also give you number of levels, right, 2 outputs, right. It will, for every level it will give you the gates that belong to that level and also the number of levels. So, we have 4 levels in this circuit. Okay. So, by that the depth of the circuit could be calculated by doing what we call as a topological sorting. So, what is the time complexity of this algorithm? I visit every edge once and I visit every node once. So, the time complexity, if n is the number of edges and m is the number of n is the number of vertices and m is the number of edges, then the complexity is order n plus m, right. So, there is actually some constant into n plus m which we call in computer science, we put it by this notation, the big O notation, which is order n plus m. So, what is order n plus m in terms of complexity? It is a polynomial algorithm and what is its complexity? It is linear complexity, right. Linear, why it is linear? Because it is linear in the number of inputs. So, what is the size of the input of this graph? It is equal to the number of vertices plus number of edges, right, that is the size of the input. So, the algorithm also takes order n plus m. So, this is a linear complexity algorithm, right. So, this topological sort is proportional to the size of the circuit, right. Now, what we need to do when we try to do an high speed circuit design is that we optimize both for the size and for high performance. I need to have the size of the circuit to be less and I should also have the depth of the circuit to be less, right. I should have small size and the depth also should be small. Then I get the best circuit, because today we are talking of performance in the notion of computer architecture is not just the timing, it is also timing plus the power that you are consuming and the area that you are consuming, right. If I make a big 1 acre chip, nobody is going to buy. This I have been repeatedly telling you in the previous class, correct, even in the previous course. So we need to make a chip that is marketable. What it means? I need cost, I need power and area, all should be within our bound. So what in essentially that means that my area should be less and I should get good performance. Unfortunately both are contradictory, right. So both are inversely proportional. If I go and say increase my area, I could get very good performance, but if I want to decrease my area, then my performance basically increases, my performance also decreases, that means the time actually increases, right. So when I start designing circuits, I should optimize both on the circuit size and also on the circuit depth, and we will try and see how these two are, what is the trade off between these two, with the example of a carry ripple adder and a carry lookup adder. Now what is addition? Addition is the most simplest operation. I am giving you two n-bit numbers, let us call it a n minus 1 to a 0, a n minus 1 to a 0, and another number b n minus 1 to b 0, and now we want to construct an addition circuit for this. The first what we will do is to construct a carry ripple adder. What is a carry ripple adder? In few minutes I will finish that, because we have learnt it in the previous course. A carry ripple adder mimics the way we do actually additions. First we will add A0 and B0, we will get a sum bit and a carry bit, that carry bit we will take it to A1, we will add that carry bit A1 and B1, that will give me another sum bit, another carry bit, that I will take on and so forth, okay. So this is carry ripple addition. So the carry ripple addition, the basic module for a carry ripple adder is what we call as a full adder, which actually adds 3 bits A, B, C, where A and B corresponds to the input bits and C is the carry bit that is coming from the previous stage, right, and it outputs 2 bits, one is the sum bit and another is the carry out bit, which is passed on to the next stage, right. We have seen this in detail, we have also implemented this in the previous course. So there are 3 bits A, B, C, this is how we calculate this carry out, which is AB plus AC plus BC, and we also have a sum bit which is A XOR B XOR C, right. We also saw how we came out with these equations, right, by just using a simple Karnaugh map, correct, or truth table. Now so this is a n-bit carry ripple adder. So we have several full adders as you see here, so full adder 0 to full adder n minus 1, we give A0 and B0 and C0, normally the C0 will be 0 to the first full adder, which will give us the sum bit S0 and a carry bit that we will pass it on to the next stage. The next stage will take A1 B1 and the carry bit from the previous stage, it will give us S1 then and also C2, which is pushed on to the next stage and so on, correct. Now when I do a topological sorting of the circuit at a very high level, first these are all, what are all the primary inputs to the circuit? All these are primary inputs to the circuit, A0, B0 till AN minus 1, BN minus 1 and C0. So let us remove all the primary inputs, right. Now the only element that will become completely shaved is this full adder 0, right. Now you remove all the elements of full adder 0, then only full adder 1 will become this, because there is a carry line that is coming here, then full adder 1 will come up, then when I remove the elements of full adder 1, then full adder 2 will come and so on. So the depth of this circuit is n. If you do a topological sorting, we will see that it is n or some constant times n, right. And what is the area or the size of the circuit? It is n times the size of a full adder, because I am putting n full adders. So, it is approximately n times the size of the full adder. Why approximately? Because there are some lines we need to connect and that will consume some area. Okay. Now, I have a circuit whose depth is n and the area is also n, right. For me this n is unacceptable, that circuit depth of n is unacceptable, because I need to work very fast. So, suppose tomorrow I want to do some cryptography algorithm, I want to do an 128 bit addition. If I take, I will take 128 units of time to do this, and say I am trying to do a voice codec, I am trying to send my thing through WhatsApp and I do not want somebody to listen, I am doing an encryption of my voice, right. I can't afford to do this type of thing, because the latency will become too high. So, I need to have very fast additions inside my circuit. So, I am just giving you an example of practical example where this n is actually unacceptable to me for say a 128 bit or so. Okay. Now, we will go and improve the speed, okay. And how do you improve the speed? Okay. So, from now do not sleep for till this, okay, you have last semester stuff. Okay. Now, who created the problem in the previous slide? Why did the circuit depth became n? Because of the carry. If that damn carry was not there, we would have been extremely happy. So, if I want to go and improve the speed, then what should I do? I should go and handle the carry properly. I should do something about that carry. So, then what we need to do? Let us take the truth table of carry and start looking at it with great interest, right. Let us take this truth table. This is the truth table of the carry, right. So, Aj, Bj and Cj, and this is Cj plus 1. Now, let us see what is going to happen here. There is something very interesting about this. When Aj is equal to Bj, your Cj plus 1 is equal to either Aj or Bj. For example, when is Aj equal to Bj? Let us take these 4 entries. When Aj is equal to Bj, your Cj plus 1 is equal to Aj is equal to Bj, right. Okay. So, the green matches with the green. Now, let us take some other. Okay. Now, when Aj is not equal to Bj, then Cj is equal to Cj plus 1. These are the 4 cases where Aj is not equal to Cj. Note that Cj is equal to Cj plus 1. When Aj equal to Bj, your Cj plus 1 becomes independent of Cj. When Aj is not equal to Bj, your Cj plus 1 is equal to Cj. So, the dependency of a carry of a particular stage, right, on the carry of the previous stage. Why the circuit depth of n came? Because the carry that I calculated was dependent on the previous stage, right, and that is why, right. So, my sum bit and the carry bit of the current stage was dependent on the carry of the previous stage. If I am going to compute the carry of the current stage, carry input to the current stage, independent of the carry of the previous stages, right, then I am going to be in a better shape, right. Now, note that independence comes for 50% of the cases, right. If my Aj is equal to Bj, the carry output is not dependent of the carry input, right. Only when my Aj becomes, so for the next stage I know what the carry is without even computing the carry of the previous stages. Are you able to follow? The carry output for me is not dependent upon the carry input of my carry input, or I need not bother about the previous stages to my right. If you keep adding from say right to left, I need not bother about the carry inputs of the previous stage or the carries of the previous stages for me to generate a carry for the next stage. I can just look at my AJ and BJ, and if they are equal, then I give a damn for the carries on to my right. But if AJ is not equal to BJ, then I am dependent on that carry. So immediately, just by looking at the truth table, please understand that I have got a 50% relief from the carry of the previous stages. Are you able to follow? Any doubts in this? Right. So this is one very interesting. I used to tell this comment, right? Obviousness is the enemy of correctness. This is a very obvious thing, but that has missed for say at least 1 decade or 2 decades before carry lookup adder came into place. Okay, but this is something very interesting to see in this truth table. Fine. So the objective of doing the carry lookup adder is to reduce the dependency of a carry to be generated in a particular stage, or carry or the sum bit to be generated, to reduce the dependency of that on the carries of the previous stages. And one relief I get just by looking at this truth table is for 50% of the cases, the carry that I generate in a particular stage is independent of the carries that come from the previous stage. Are you able to follow? And the remaining 50% I need to depend upon this. Fine. Okay. Now please note this down, please have this truth table with you, please write down this truth table in your in your notebook, and also this statement, this if then condition. So let us do this simple table here. If my AJ equal to BJ, then I have two cases, case 1 and case 4, and AJ equal to BJ and AJ is 0, BJ is 0, then what would be the carry? It will be 0 for the next stage. So AJ BJ comes in this stage, right? What will be my carry for the next stage? It is 0, right? That means I call it as kill. I kill the carry, then I do not allow the carry to, if one goes then it says I am propagate. So I say I kill. When AJ equal to BJ, irrespective of the carry of my stages to the right, the carry I generate for the next stage is 0. So I call that status as kill, right. If my AJ equal to BJ, then I do 1. The carry that I propagate to the next stage is 1. So I generate a carry for the next stage. When my AJ is not equal to BJ, I just take the carry from the previous stage that comes from the previous stage and pass it on to the next stage. I call these two cases as propagate, right. So the moment I get AJs and BJs, immediately I will know what is the status of the carry that I am going to pass on to my, each stage will know what is the status of the carry that it is going to pass on to the next stage, right. The moment I get my inputs, that n bits, right, A0 to An minus 1 and B0 to Bn minus 1, each stage can immediately understand, right, what would be the status of the carry that it will pass on to the next stage, right. If it sees both as 0, then the status is kill, it is going to give a 0 as a carry to the next stage. If both the inputs are 1, then it is going to give a 1 to the next stage, so I call it as generate. If both the inputs are not equal, then it is going to take the carry from the previous stage and give it to the next stage. I know that it is going to be a propagate. So the moment these two n bits arrive to the circuit, immediately every stage can determine the status of the carry that it is going to pass on to the next stage. Okay, able to appreciate this point. So just note down this particular table. So 0 0 means the status of what? Status of the carry that I am going to pass on to the next stage, right. It can be kill, it can be propagate, it can be generate, or it can be propagate. So what is a simple circuit that can realize this? So let us say kill I can encode it as 0 0 because I have 3 different status. So, at least I need 2 bits to encode it. Kill will be 0 0, generate let it be 1 1, and let us say propagate is 0 1. So, these are the status bit S1 S0. So, let us draw that here. So, this will be S1 S0 0 0 0 1 0 1 1 1. So, AJ BJ and this is the status. Please note that S1 will be, so S1 of J will be AJ and BJ, correct, and S0 of J will be AJ or BJ, correct. Where this is the encoding, kill means 0 0, generate means 1 1, propagate means 0 1. I need 2 bits to encode this status because I have 3 status, correct. So, the moment the A's and B's comes, the n bits come, immediately I can go and generate the status of the carries that I want to pass on to the next stage in one stroke. So, I need n AND gates and n OR gates, which I will provide, and in one shot immediately it will give me the status of the carries. So, it will give me a 2 bit output which will essentially tell me whether it is kill, generate or propagate, and that just takes one gate delay, right, as you see. Okay, fine. Now, this is very interesting. Now, this is stage J, this is stage J plus 1, okay. This is stage J plus 2, okay. Let us say, so if stage J plus 1 is kill, what will be the carry? If the stage, so let us see this, what will be the carry of, so let us draw this entire thing. Okay. So, let us draw say 4 stages, okay. Now, the A's and B's have come here, A0, B0, A1, B1, A2, B2, A3, B3, right. Okay. So, there is always 0. So, what you get here is kill, right, and you generate, this is what we call it as C0, okay. Now, there is a status that we have generated for each, okay. So, I have a status x0, x1, x2 and x3, okay, right. Right, I have x0, x1, x2 and x3. Now, suppose let us say this is 0 0. So, let us take the 4 bits here, give me some random 4 bits, give me some 4 random bits here, 0 1 and another, okay, right. Now, so A0 and B0 are 0. So, what is the status of this? This is kill, okay, and what is the status of this? This is generate and this is propagate and this is what? This is also propagate, fine. Now, if I do, so what is the carry here? Since this is kill, this carry is going to be 0. So, since this is kill, this carry is going to be 0. Since this is generate, the carry is going to be 1. Since this is propagate, this carry is going to be 1. and since this is propagate, the carry is going to be 1. Okay. So now I can go and say that this is 1 by looking at this G. So from every propagate I can go to the last, but if this was kill, say for example if this is kill, then this would have been 0, this would have been 0, right. So at any point when any of the stage is kill, from there it starts sending 0. If any of the point is G, then it starts sending 1, right. So if I have a sequence of propagates like this, for me to actually find the carry I need not go till the end, but I need to just to go to the point where I see a generate or the first thing that I encounter. So from this propagate I go back towards my right hand side, and if I find the first one is a generate, then I know all these are 1s. Okay, are you able to follow? So that looking back operation is what we call as this operator called star within brackets. Okay. So now we will see this. If my stage j plus 1 as kill, right, then irrespective of what is happening in my right hand side, I am going to have kill completely, right. If my j plus 1 is kill, that is any stage is kill, then I do not allow anything to propagate from the previous side. So whatever be my status of xj, this operator will just kill. So all that is going to propagate from this point is going to be zeros, right. If my j plus 1 is generate, right, if my j plus 1 is generate, all that I do not care about what is happening to my right, all that I am going to propagate from this end is going to be G. But my j plus 1 is propagate, please note that, and my previous stage was kill, then I know that it is going to be kill. If my previous stage was generate, I know it is generate, but if my previous stage was propagate, then I go and propagate. Okay, right, you understand this? So just I will repeat this. If the status of my j plus 1th stage is kill, irrespective of what is going to be on my right hand side, I am going to just say it is going to be kill, right. So I am independent of this. If my previous stage was generate, if my current stage is generate, then I do not care on the right hand side, I am going to push generate. But if my previous stage was kill and I am propagate, then I make myself as kill. If the previous stage was generate, I make myself as generate. If my previous stage was propagate, then I remain to be in a propagate state, right. So now what I do is I get the status of every carry that I contribute to the next stage just by seeing this A's and B's. Then what I do is I do a prefix computation on these carries, on the status, right. So what I do is yj, for every stage j I compute yj is equal to this x operator, x0 operator, x1 operate x2 till xj, right. So if I do this operation and if I get yj is equal to k, then I know that the carry for my stage is 0. If I get yj is equal to g, then my carry is going to be 1. And note that your yj after this computation will never be propagate. Why? Because we know that x0 is kill, so this is always kill. So the kill with anything else when I go will land up with kill unless I see a g there. So at the end your yj will never be a propagate. Okay. So I just stop with this particular slide today. I want you to think about this, right, that I get the carry status, namely xj's, and from the carry status I want to go and find out what would be the carry itself, and for that I go and do this associative operation, okay, right. So I go and do this operation, and later I will show that it is going to be associative, right. So I will continue with this in tomorrow's class, but I just want you to think about this particular slide. Kindly note it down and think about this slide, so that we can continue from this slide tomorrow, okay.